Hi everyone. My name is Murgayu Kosh, and um, I am I'm just making this video because I realized something today, and um, I wanted to write it down here so I would A, remember, and B, share it with y'all because I feel like this is something we don't really recognize when we're doing chemistry. So this is for chemistry actually. Um, but this is the concept of the molar mass, which we represent with a capital. Um, which we can represent with a capital. I actually write two M's to differentiate it from molarity, which is moles per liter. But we're going to do two M's for molar mass. Um, so often when we're trying to figure out molar mass, what we just do is we kind of let's go to the periodic table, ptable.com. What we often do is we just go to ptable or the periodic table and we just say, oh, carbon has a molar mass of 12.01 grams per mole, or nitrogen is 14.01 grams per mole. But really, that doesn't, I've never really thought about it, and that's something that's strange to me. I don't know why I haven't thought about it. Um, I realized that today after thinking about it for a little bit longer. But if we think about it, we the molar mass it has to be connected using Avogadro's number, n sub a, which is 6.022, I believe, times 10 to the 23. Yes, 6.022 times 10 to the 23rd. And if you want to put units, it's elemental entities, whatever it is. So whether it's, I'll write elemental entities, elem, I'll put abbreviations, elem, ent, per mole. So whatever that is, so whether it's atoms, 6.022 times 10 to the 23 atoms, or ions, or formula units per mole, or even molecules per mole. So that means if I say I have, just like if I say I have 2 dozen eggs, if I say I had a mole of eggs, that would be a whole lot of eggs. That would be 10 to the 23rd times 6.022 eggs, which is very, very weird. And the reason why we use moles for atoms and these very small particles is because they're so small, there's going to be a lot of them, right? But why is it that I can take atomic mass units from the periodic table and somehow go to grams per mole? That never made sense to me until I thought about it today. So let's try and prove this is kind of like a proof. So let's what we're trying to prove essentially, prove essentially is that atomic mass units per atom is equal to grams per mole. Now, how do we go about doing that? Well, if we look at the periodic table, for each element, we can assign its average atomic mass, P, in AMU per atom, right? And really, I should have said this. The average atomic mass, that number, whatever is, I'm referring to it as P. So I'm gonna define P right here for you. P is equal to the average atomic mass in AMU, or we could really it's AMU per atom, because if I don't define it that way, the unit conversion is not going to work. And it's also equal to the molar mass in grams per mole. But how does that work? That doesn't really make sense, does it? So we're saying that P AMU per atom, and the P just stands for periodic table. So that's not an official symbol. I'm just making it up. But essentially, for example, P for magnesium would be 24.330, right? Or 24.31. But it can be used for any atom because the same process we can apply for any atom, for any element on the periodic table, and we can define its molar mass. So for P AMU per atom is equal to P grams per mole. Somehow we need to convert this to P grams per mole. Now I'm going to leave some space. Well, Actually, let's keep that there. We start off with our left-hand side. This is going to be kind of like a mathematical proof, but LHS, left-hand side, equals P mu per atom. Now, we have to somehow convert AMU to grams and atoms to moles. So we need a conversion factor that cancels AMU with grams on top, and we need a conversion factor that cancels atoms with moles on the bottom, right? And we need 1 mole. We can't have multiple moles. We could have multiple moles, but that's not the point here, right? So essentially what we're trying to do is show that these AMUs will cancel and these atoms will cancel, and that'll leave us with P grams per mole. But there's a problem. We can't just multiply this. We need to figure out what this, there has to be a number here. So the way we can find that out is by searching up how many grams are in 1 AMU. How many grams are in 1 AMU? And a quick Google search shows that it's 1.66 times 10 to the 24. So 1.66 times 10 to the 24 grams are in 1 AMU. So that's the conversion factor for that. And here, based on Avogadro's number, we know that there's 6.022 times 10 to the 23rd atoms per mole. And essentially, that means if we multiply these out, this won't just be P grams per mole, this will be P grams per mole times 1.66 times 10 to the negative 24 times 6.022 times 10 to the 23rd. But that's a problem because it's not a problem, as we'll see, but just at first glance, that looks like a problem because we said that P AMU per atom has to equal P grams per mole. Otherwise, our assumption that we make whenever we say, oh, oxygen has a molar mass of 16, has a molar mass of 16 grams per mole, that would be wrong, that assumption, because if this proof doesn't hold true for all elements, then that's a problem. So obviously it has to be true. And the reason why, if we actually do this math and we calculate it all out, 1.66 times 10 to the negative 24, I'll just do it on Google's calculator. So if I do 1.66 times 10 to the, what was it, negative 24, and I multiply that by 6.022 times 10 to the 23rd, look at that, I get 0.999. It's actually, the answer is essentially, it's just 1. And why is that so interesting? Because that means that's just P grams per mole. And therefore, that equals our right-hand side. And because our left-hand side equals our right-hand side, we have essentially proved what we set out to prove, so QED, okay? So we have essentially proved that if we look at the periodic table and take atomic mass units per atom, and we can actually just assume that to be the molar mass based on this relationship. I just wanted to go through this. I don't know if it's just me or if other people don't realize this as well. I feel like other people don't, because we kind of just blindly look at the periodic table and we assume, oh, it's just the molar mass, right? But I think that understanding this dimensional analysis and understanding how these units cancel to produce grams per mole is interesting. Now, I want to draw your attention here for a second. It's so interesting that the product of these two equals 1. What that tells me is that these two are reciprocals. That means 6.022 times 10 to the 23rd is the multiplicative inverse of 1.66 times 10 to the negative 24. It means if I do 1 divided by this number, whatever that number is, if I do 1 divided by that, I'm going to get Avogadro's number, which suggests to me that's probably, I don't know if that's how he calculated it, but that would make sense, right? To make our lives more convenient, what we do, so we can work with moles, because remember, we can only compare moles of atoms. We can't compare grams of carbon to grams of hydrogen, because as my chemistry teacher, Mr. Rogers, says, you can't compare grapes to watermelons, because the mass of a grape is obviously not the same as the mass of a watermelon. But if we compare to number of fruits, then we can obviously compare, okay, if I have 5 grapes to every 10 watermelons, then I can compare that. And then I have to convert back to grams. So that's why it's similarly in the scale of atoms and particles, we use moles, right? So that's why we need to get from AMU, or to get from atoms to moles. And that's why we can go from the average atomic mass on the periodic table, which is in AMU per atom, and we can assume that to be grams per mole based on this relationship. And what that tells me is this number, it's the only number that could make this equation true. If Avogadro's number was something else, it wouldn't be true. Maybe that's actually how he found it, because if we had, I don't know, once again, I don't know if that's how he found it, I'm just guessing. But if I had P AMU per atom, and this, obviously, this is something we've defined, atomic mass units, that has to be true. But say this was just X, we didn't know what this was. Say this was just a variable X, and we're trying to find X, and we set this equal to P grams per mole, because it has to equal P grams per mole to make our lives convenient, so we can just look at the periodic table. That would have to be X, right? So if we solve X, we know that essentially what would happen is we would have P times 1.66 times 10 to the negative 24 times X grams per mole equals P grams per mole, right? Because this is the right-hand side of our equation, so this is the right-hand side of our equation right here, and our left-hand side of the equation, if we, all the units have canceled out except for grams per mole, so I put that there. The P is still there, so I put the P there. The 1.66 times 10 to the negative 24 is there, and then the X from the X atoms per mole. So I have an X there. Now, if I solve for X, guess what happens? I can cancel the P from both sides, divide the grams per mole from both sides, and I get 1.66 times 10 to the negative 24 X is equal to 1, because nothing else is left on the right-hand side. So by definition, X will be the reciprocal of that 1.66 times 10 to the negative 24, and therefore, as we've shown, 1 divided by 1.66 times 10 to the negative 24 is Avogadro's number, 6.022 times 10 to the 23rd power. So I think that's actually pretty interesting, and I can't believe I didn't realize it earlier, but I think it's a pretty cool relationship. That's something we tend to miss, and we just assume, oh, moles are just, I think we understand that moles are meant to be a way to count them, but I don't think we understand this mathematical relationship and why we're just able to look at the periodic table and go, oh, it has an average atomic mass of, I don't know, 54 or whatever. I don't know. I don't even know if an atom has an average atomic mass of 54. Well, yeah, manganese has 54.94, but that's the point is, look at manganese. Now we know why it's 54.94 grams per mole, because of the fact that AMU can be converted to grams per mole using the ratios, using these identities of Avogadro's number, as well as what we've defined to be an AMU. We've defined one atomic mass unit to be 1.66 times 10 to the negative 24. Anyways, thank you for watching. If you think I made a mistake, because I always make, seriously, I always make mistakes, please point them out. In the comments, email me, whatever. I'll put my contact information in the description. Thank you. I hope you found this useful, because really this was more an effort of me just to go through my ideas and just express them that way, because I do feel that putting my ideas down helps me better understand them. So at the same process, I think that if you understand them better, definitely doesn't harm anyone. Yeah, thank you.